So let's start with the next topic, that is linear regression. Now this is one of the very important and very useful topic which very extensively used in the AI and ML also. So linear regression, the use of linear regression is to predict a trend in line or predict the value of a variable dependent from the value of another variable which is independent by fitting a straight line through the data. Linear regression is used for finding linear relationship between target and one or more predictors. There are following types of linear regression: simple linear regression, polynomial regression, support vector regression, decision tree regression, random forest regression. Now, simple linear regression is useful for finding relationship between two continuous variables. One is predictor or independent variable and the other is response or dependent variable. It looks for a statistical relationship between not deterministic relationships between two variables is said to be deterministic if one variable can be accurately expressed by the other. Now, for example, using temperature in degree Celsius, it is possible to accurately predict Fahrenheit. A statistical relationship is not accurate in determining relationship between the two variables. For example, relationship between height and weight. So these are the various applications where linear regression can be used. The core idea is to obtain a line that best fits the data. The best fit line is the one for which total prediction error, all data points are as small as possible. So if they are more close to the line that you draw for your regression analysis purposes, you will be able to get a better understanding of that. Error is the distance between the point to the regression line. Regression models are used to predict a continuous value, predicting prices of a house given the features of house like sizes, price, etc., and is one of the common example of regression. It is supervised technique. Now this is one of the most common and interesting type of regression technique. Here we predict a target variable y, capital Y, based on the input variables x, capital X. A linear relationship should exist between a target variable and the predictor, and so comes the name linear regression. Now let's try and understand with an example now. Consider predicting the salary of an employee based on his or her age. We can easily identify that there seems to be some correlation between employee's age and salary. More the age, more is the salary. That is a normal. It is not mandatory, but that is the general norm. The hypothesis of linear regression is y is equal to a plus bx. Y represents salary, x is employee's age, and a and b are the coefficients of equation. So in order to predict y, that is salary, given x, that is age, we need to know the values of a and b. So you must have seen these kinds of graphs in your school or colleges where you have learned this linear regression, and the formula that is y is equal to a plus ax plus b, that also must have seen. Now while the training and building a regression model, it is these coefficients which are learned and fitted to training data. The aim of training is to find a best fit line such that cost function is minimized, because our focus is that cost function should be minimal. The cost function helps in measuring the error. During training process, we try to minimize the error between actual and predicted values, and thus minimizing the cost function. In the figure that we have seen in the previous slide, the red points are the data points, and the value line and the blue line is the predicted line for the training data. To get the predicted value, these data points are projected onto the line. You can go back and see. So this is the blue line that you can see, and the red data points are there. So that is how you can see the how the line is drawn. Now here our aim is to find such values of coefficients which will minimize the cost function. The most common cost function is mean squared error, MSE, which is equal to average squared difference between an observation's actual and predicted value. The coefficient values can be calculated using gradient descent. To give a brief understanding in a gradient descent, we start with some random values of coefficients, compute gradient of cost function on these values, update the coefficients and calculate the cost function again. This process repeated until we find a minimum, that is for the individual, the developer or the user, to decide that which is the minimum that he's expecting, and that will be the minimum value of your cost function. Now, polynomial regression. In polynomial regression, we transform the original features into polynomial features of a given degree and then apply linear regression on it. Consider the above linear model, that is y is equal to a plus bx is transformed to something like y is equal to a plus bx plus cx square. So you can apply, in the case of polynomial, then you can use this kind of equation. It is still a linear model, but the curve is now quadratic rather than a line, because here it is the another factor that you are going to consider. Scikit-learn provides polynomial features class to transform this feature. If we increase the degree to a very high value, the curve becomes overfitted as it learns the noise in the data as well. Now, support vector regression also can be used. In SVR, we identify a hyperplane with maximum margin such that maximum number of data points are within that margin. SVRs are almost similar to SVM, that is support vector margin classification problem, which we'll be discussing in the later topics. Instead of minimizing the error rate as in the simple linear regression, we try to fit the error with a certain threshold. Our objective in SVR or support vector regression is to basically consider the points that are within the margin. Our best fit line is the hyperplane that has maximum number of points. You can see here also at least some points that we are seeing within that hyperplane. So data points within the boundary is known as the support vector machine. Support vector. So this completes our linear regression part 1. Thank you.